All right, welcome to the last set in chapter 9, or the last lesson on independence probability intro, which we're looking at independence. Now, independence is a funny word and a funny idea, but I'll try and explain it in a easier way. With this little passage here we're going to read. So in probability, we say that two events are independent if knowing one event occurred doesn't change the chance of the other event. For example, the probability that a fair coin shows heads after being flipped is a half. Everyone knows that. What if we knew the day was Tuesday? Does this change the chance of getting heads? Of course not. The probability of getting heads, given that it's a Tuesday, is still a half. So that would be PR heads given Tuesday is still a half because the day can't influence the flip. So the result of a coin flip and the day being Tuesday are independent. Right? So independence is tied up with conditional probability. Knowing it was a Tuesday didn't change the chance of getting heads. Not every situation is this obvious. What about gender and handedness, left-handed versus right-handed? It may seem like a person's gender and whether or not they are left-handed are totally independent events. But when we look at the probabilities though, we see that about 10% of all people are left-handed, but about 12% of males are left-handed. So these events are not independent, since knowing a random person is male increases the chance they are left-handed. Today's big idea is that we check for independence using probabilities. Right? So we're not going to check using logical thinking, we're going to check using a little formula. And this is the big idea here, that we can do this. All right? So two events are independent if this is met. Okay, so the chance of A given B is equal to the chance of A. So this basically just says, knowing if B happened doesn't actually help us with A happening, which is what happened in the first example. Knowing it was a Tuesday didn't help us knowing that it was a heads or not. So knowing it was B doesn't help us knowing A. Okay, so if two events are independent, this is true. Okay, so instead of using conditional, we'll use the substitution that we came up with last lesson. So we can see here that intersection, oops, I needed a little bit more room. Move that over there. Oops, bear with me, there we go. So this is the formula we will use to calculate independence. So A intersection B equals A times B. All right, or we could use this one if we wanted to, but this one has a bit more complexity to it because of the conditional part of it. Okay, so without any further ado, let's have a look at a few questions. So here is the ages and social media question from last lesson, but we've been asked something different. 500 people were questioned and classified according to age, blah, blah, blah. Do you regularly use? So we've got ages here, yes, no, social media. Is the regular use of social media independent of the respondent's age? All right, so we need to know if this is true. So we'd have use given age is equal to the chance of use. All right, so this is what we're going to try and calculate. So we'll use this formula here. We need to know the intersection of use and age, and we need to know the chance of use, and we need to know the chance of age. Okay, so if that's not confusing enough with all the symbols and letters, hopefully we can get our way through it. All right, so we know from the Carnot table that the intersection between these two is this one here. So we have 200 out of 500, because it's the total probability, equals the chance of use. The use one is here, 240 out of 500, multiplied by the age, which is this one here, 300 out of 500. I think I may have just got them around the wrong way. Yep. This one, the 240 out of 500 is the age because it was down the age column, and the 300 out of 500 was the use because it was across the use row. So sorry about that. All right, so now all we have to do is to calculate this sentence out and see if it works in the end. All right, so 200 out of 500 is 0.4. 240 out of 500 is 0.48. 300 out of 500 is 0.6. Calculate that 0.48 times 0.6 and we get 0.288 as our answer. And we can see here that 0.4 does not equal 0.288. Therefore, use is not independent. I don't know how to spell this. Independent on age. And if we think about it logically, that makes sense. It doesn't help us. Sorry, age will tell us people who use social media more. It's not irrelevant to the other piece of information, right? So that made sense. But we need to use the formula to show it using this idea here, all right? Another example we can look at is this one here, where an experiment consists of drawing a number at random from 1 to 8. So we have an A event, a B event, and a C event. We're just going to calculate the independence of A and B, A and C, or B and C. All right, so what are the chances of A happening? Well, A is 1, 2, 3, 4 out of the 8, so A is a half. What are the chances of B happening? B is 1, 2, 3, 4 out of 8, so B is a half. And what are the chances of C happening? Well, C is 3 out of 8, and that doesn't simplify, so we leave it as is. Now, we need to know what the chances of A intersection B are. We need to know what the chances of B intersection C are, and we need to know what the chances of A intersection C are. All right, because these are tied up in our little formula here of independence. Okay, so let's have a look at those. All right, so to calculate intersections, we need to know how many results are in both A and B. So we've got 1, 3, so that's 2 out of 8, which is the same as a quarter. In B and C, we have, what do we have? There's no crossover in B and C, so that's 0. And then in A and C, we have 1, 2, 3, 4. We have that 4 there, so that's 1 out of 8. All right, so now we know those, we can calculate independence for each of these questions. All right, so we need to go, we'll start with A and B. So we need to know that a quarter is equal to the chance of A times the chance of B. So that's a quarter equals a quarter. Good. QED. A and B are independent. Having trouble today with independence. All right. For B and C, we need to know that B and C, 0 equals a half multiplied by 3/8. And we can see there that we are not going to get the independence we need because fractions multiplied by each other don't equal 0. So we'll put that there. So that's 3/16. All right, so B and C are dependent. And the last one, A and C, so we can see that A and C is an eighth. An eighth has to equal a half multiplied by 3/8, and you can see that I have a numerator of 3, so I'm not going to get my independence. 1/8 does not equal 3/16 either. All right, so A and C are not independent either. All right, so there was only one event independent there. All right, so to calculate independence, we need to know individual probabilities plus intersections. And then we're just using this little formula here to calculate it. All right, so it really tests your thinking. You can't just look at it and say, oh, they're definitely independent. All right, so something else we can do is also to look at the idea of mathematical independence versus physical independence. All right, now what I mean by that is you can see here that we have rolling a die, and we have an A event and a B event and a C event. So A is the first roll, shows a 4, B is the second roll, shows a 4, and C is the sum of the numbers showing is at least 10. Okay, so let's first of all look at this one. Are A and B independent? So we can see that A is a 1 in 6 chance, B is a 1 in 6 chance, and it has to equal the intersection of them both where both numbers are a 4, which is a 1 in 36 chance, and you can see there that 1/6 times 1/6 equals 1 in 36. So A and B are independent. Okay, because they were two different rolls, they're physically independent because the second roll can't influence the first and vice versa. If they're physically independent, then they must also be mathematically independent. Okay? I'm just really having trouble with independence today. Independent, physically independent. Now, what about A and C? So A and C, A is the first roll showing a 4, and C is the sum of the numbers showing is at least 10. All right, so now if we drew a two-way table for this roll, we would know that there were 6 results that add to 10. All right, so we have C is 6 out of 36 chance. Okay, looking like that. A, we know, is a 1 in 6 chance. PRA equals 1 in 6. So I have 1 in 6 multiplied by 6 in 36, and it has to equal the intersection, which was the chance of rolling a 4 in the first roll and also adding to at least 10. If you'd drawn your two-way table, you would know that the combinations were this, 5, 5, 5, 6. Now we're including everything above 10 as well because it said at least 10. What's it? 6, 4, sorry. 6, 4, 6, 5, and 6, 6. They were our 6 combinations, and you can see that only one of them meets the A condition. So we have a 1 in 36 chance of intersection A and C. Okay, so this 1 in 6 times 6 in 36 has to equal 1 in 36 to prove independence. If you remember how to multiply fractions, you can cancel those out, and you end up with 1 in 36 equals 1 in 36. All right, so this one has been proven. A and C are independent. All right, independent. All right, so A and C are independent. All right, so the last example we'll look at where we are able to use our ideas of independence and manipulate them slightly. All right, so suppose that a probability that a family in a certain town owns a television set is 0.75, and the chance that a family owns a station wagon is 0.25. Now, logically, we can think to ourselves, surely there's no dependence on owning a station wagon to TV sets, but it tells us if these events are independent, find the following probabilities. A family chosen at random owns both. All right, so both is the intersection. So this is PR, TV, and station wagon. We want to find that, and it says find the chance that a family chosen owns at least one of these items. So that would be PR, T, union, because that would be at least one is or TV or station wagon. All right, so we're finding both these things here. Now, we remember from our our independence test that PR T union S equals PR T multiplied by PR S, and this we're able to use this because they told us the events are independent. So all I have to do is multiply T times S, and I get my intersection. So this is 0.75 by 0.25, and that's going to equal 0.1875. 0.1875. So that's my intersection. My chance of owning a TV set and a station wagon is 0.1875. Now to use to find the union, we need to go back a few lessons to our formula that looks like this. Actually, I'll just write it next to the problem. PRT plus PRS minus one of the intersections. All right, and funnily enough, I know all of those things. This one is 0.75, this one is 0.25, and this one is 0.1875. So plus, minus. All right, so just add them together, and I'm going to get 0.8125. So there is a 81% chance that the family owns at least one of those two things, which we know is, in a certain town, that seems quite logical because a TV set almost everyone has. Station wagons, this town's obviously got a lot of families. All right, so in closing, this independence idea runs off conditional probability, where independence shows that one event is not conditional on the other. And we use this formula to calculate mathematical independence, all right? And we can also manipulate it if we are told events are independent and find intersections and then use those to find unions of sets.